Okay, so this is what a regular sine graph looks like. The goal of the second half of the unit now is to try to talk about what would happen if you were to do, you guys remember the idea of how you take a function and put it inside another function? That's like this notation I have down here, like the f bracket g of x notation. What we want to do is we want to talk about what's going to happen to a graph if we were to put functions inside other functions. That makes sense? And we've actually already talked about one of them. We talked about the one where you add numbers. I'm going to hop over here to these last ones here, f of j of x and j of f of x. What would f bracket jx be based on these equations I have up here? What does this notation mean to do?
Have j of x and then put that inside of x.
Okay, so what is j of x? Well, j of x is x plus 2. And I'm going to take that and I'm going to put that inside of the sine one. Good. But I'm going to make sure I'm very clear. The x plus 2 is inside the brackets. Okay. We talked about this for sure, like the day I was still here. What does a plus 2 inside a function do? Does it move it that way, which is pointing left? No, that's right. Right or left? Good. It moves it left. Okay. And let's just test that then. Go to your y equals. Type in sine of x plus 2. I'm just going to make it be bolded black. And hopefully what should happen is my graph should be slightly behind. Does that make sense? This crest right here is actually going to move back too. This bottom crest back here, so the crest is a shrub, it's been moved back too. Does that make sense?
How did you write that on the y?
So it's sine of bracket x plus 2. So I shoved the x plus 2 inside the function. And what it does to the graph is it slides it backwards. We call that like a translation. If you guys remember the term congruent, this is a congruent graph. All that's happened is you've taken the one graph and you just kind of slid the wave backwards. Does that make sense? Let's try this one here then, because we've also done this one. What if I asked you for j of f of x? What does that mean?
Sine of x, put that inside x plus 2. Sine x.
Okay. What's the difference here between this one and that one? Yes, because what's happening here is really we're not adding the 2 in the brackets, we're adding the 2 after the brackets. So remember my vending machine analogy. This one here is like you put money in the vending machine, and then after you're done, you always get 2 more. This one right here is before you start, you get 2 more. This one should move it up. So I don't even write this out here. This one will move it left by 2 that way. This one should move it up by 2 that way. Let's just make sure and test it. So take the plus 2 from being inside the function, put it on the outside. So here's our first wave, and then now here's the exact same wave, and hopefully you guys will agree. This is a congruent graph. It's like literally the exact same, only it's been shifted up. Does that make sense? Okay. On the video that I wanted you guys to watch, basically I walked you through 2 other possibilities. Now these other possibilities are not congruent anymore though. Okay? It's going to change the graph, but they won't be like a sliding the graph around. What they might do is it might flip the graph upside down. It might kind of alter the perception of the graph. So let me try some of these other examples with you. What would f of g of x mean based on this stuff right here then? Well, it means take the negative x and put it inside the sine side. So let's graph that, see what it does. Just need to restart my calculator. So here's the regular graph. And then there's this graph here. What's happening? It's actually reflected. I like to use a lot of hand signals here, but it's been reflected like this. It's been flipped over. Now this graph is maybe not the easiest one to see, so I'm just going to make a subtle change here. Let's change it from sine. Let's change it to something different. Let's make it sine's not a good function. Let's use We'll think of something good here. It's a good function to try. That one won't work. You know what, I'm just going to do something ridiculous. Let's go x to the power of 3 plus 7x minus 8. And what I want to do on the bottom graph is I want to make it negative x to the power of 3 plus 7 with a negative x minus 8. Do you guys see how it's the same graph? Only rather than using x, I'm using negative x. Okay. What I'm hoping we'll see here is the graph is going to flip this way, side by side. So hopefully we'll see that. I'm just going to rebold this guy. So here's my first graph. I guess I don't see much to it. Do you guys see how that second graph is just been flipped over the, we say it gets flipped over the y-axis. Does that make sense? That's what happens when you take a negative and throw it inside the function. Basically, all of your x values are now negative. So you see on this thin graph right here, your x values were all positive x values. While by making it a negative on the inside of the brackets, it makes all of these values become on the negative side. Sine's not a great graph to show that one with because sine was kind of symmetrical either way, so that might not be the best choice. Let's try this next one here. G of f of x. What would that mean about the function in terms of like writing it out? It would be negative sine x. Okay. If putting a negative inside the brackets makes it flip this way, I like to use my hands a lot. Any idea what a negative outside the function is going to cause it to do? Causes it to flip head over heels. I'm going to try a different function to illustrate though. I'm not going to use the sine one again. Let's just use an x squared graph because you guys know that one. If I gave you x squared as one of your functions, and then I asked you to do negative x squared, I'm just going to make sure it's really clear that negative is outside. What does a negative leading coefficient do to a graph? Well, it makes it go upside down. Here's the first graph. Here's the second graph. You can see how it's flipped head over heels. I'm just going to try it one more time with just some other random looking graph just to help prove my point. Let me try having x squared plus x plus 8. And then down here I'm going to make it negative x squared plus x plus 8. So you see how it's the same function, but outside of all of it there's a negative sign? What this should do then is take my original function being up here. You see how it's way down there? It's been flipped like in a mirror head over heels. Does that work? One more time. What if I were to take that same function though and make it bracket negative x squared plus negative x plus 8? What would that do? Flip it side over side. This one you probably won't see quite as much, but see how this one's just kind of off to that side right here? And the second one gets flipped over onto this side right here. Make sense? Those are the subtle differences I'm trying to discuss here. Is put a +2 in the brackets, it moves it side to side. Put a +2 after the brackets, it moves it up or down. Negative signs cause graphs to reflect, is the word we use. Okay, two last examples here. Let's say I gave you f of h of x. So what does this notation mean based on what I've got up here? Well, it means take a 2x and shove it inside the f notation. So it was supposed to be sine of x, it's now sine of 2x. I'll go back to doing sine graphs for this one, that'll work well. So let's just do a sine of x graph, and then for the one below it, let's do sine, but rather than x, let's make it a 2x, and compare what it does. So here's the first one. Yes, it's squished in. I like the analogy of an accordion. Okay. You used to have a very pulled out slinky or accordion, and by putting that 2 there, it squished it in. And so that's why it's happening a lot faster. That's why you see more of it. Does that make sense? Let me just try another function just to try to.
Like side 6.
Let's try it. So if I put a 6 there, here's the original graph. What this next one's going to do is it's going to squish it in 6 times as much. So it's going quite intense there. Does that make sense? Actually, while we're talking about that, let's say we used, you know how we just used 6? 6 kind of squished it in 6 times as much. What if I were to use the number 0.5?
Did you like make it longer?
Yeah, what's going to happen is rather than squishing it in by using a decimal number, it should pull it out. It's almost like taking a spring or a slinky, and my daughter got a hold of it and just like pulled it, you know, like to a straight line. So here it used to be kind of curvy, and then here it's a very, very long sort of wave because it's been pulled very far out. Okay, one last one here. H of f of x. So here we were putting the 2 inside this function here. Now it's on the outside, so now it's 2 sine x. What happened now? Here's our original sine wave up and down. Here's the exact same graph.
It just looks like it's long.
It's taller.
Yeah.
It's taller. So you know how on the previous one we were kind of squishing things in, like an accordion? Here it's like we pulled it up. If you think of this wave as being like a surfer wave, the waves are now taller. The name for that was amplitude, by the way, if any of you recall that. We're making the graph bigger in that direction. What would happen if I took this and rather than making it a 2, I made it an 8? Well, here's your original graph. Now I made it an 8. What happened to the graph? I mean, it got way.
But it still has to stay like
It has actually the same intercepts as the other graph, eh? Like, see how it kind of crosses the same points? But this part right here, it's like it's been pulled way up. Does that make sense? Okay. Those are the translations that I need you guys to know. Let me just write them out on the slide here. Okay. If I were to give you f of x plus 2, that means it's going to move the graph that way. The graph would be the exact same graph, but you're just going to translate it. If I were to ask you for f of x minus 2, it just translates the graph that way. Does that make sense so far? We also talked about what if I take the function and then well afterwards, what if I add 2? What does that do to a graph? Remember what happens if you do a plus 2 way afterwards?
Pick it up.
Good, yeah, up. And f of x with a minus 2 would move it down. That's a good idea. We'll be writing this on the back of your formula sheet. You will get to know this, I promise, over the course of the next little while. I guarantee it. You'll just start to know these. Those are all congruent translations, and those are the ones we talked about in the topic on translating. But here's the other possibilities then. What if I were to give you f of a negative x in brackets? Do you remember what that did from earlier today? Good, yeah, it does a, let's call it a reflection. Although flip is pretty good too, I guess. And it flips it side to side. If I give you a negative in front of the whole function, it does a reflection as well, only rather than doing a side to side reflection, it does like a top to bottom reflection. All right, guys. Anybody want breakfast? It looks like yogurt and bananas today. Thanks, guys. You guys still with me so far? Does this make sense-ish? Probably makes way more sense if you watch my video, but you're okay? Okay. The last examples then are, what if I throw, say, a 2 in front of the f of x? Remember what that did to the graph?
Made it taller.
Yeah, we have a term for that. We're going to call that a stretch. Oh my goodness, stretch. I can spell. Stretch. Basically, it's going to make it taller. What if I did a f of 2x?
Makes it longer.
No, actually, the 2 squished it in. So this one right here, I guess it made it taller that way. This one right here, it kind of did like a compression. Is probably the better word I could use. That'll work, squish. And it kind of squished it in. That make sense? If we were to have done f of, like, say, 0.5 of x, that's actually where it pulled it outwards. Everything got pulled outwards. That's supposed to be 0.5. The one example I didn't show you is what happens if we put, like, say, a 0.5 in front of the f of x? Anybody have an idea what that might do? Yeah, it makes it shorter. I just watched a video with Kingsley Ann on, it was Curious George, actually. Side note here. And Curious George went into, like, one of those fun houses where they have all those different types of mirrors that make you look tall and thin and fat and stuff like that. You guys get what I'm talking about, a fun house there? And Curious George, being a little monkey, was learning how different mirror types change your body size. I kind of imagine that right here. If I give you a 0.5 f of x, what it's going to do is it's going to be a mirror that makes you shorter. Does that make sense? So this is a mirror that makes you taller. This is a mirror that makes you thinner. This is a mirror that makes you fatter. Does that make sense? And this is a mirror that makes you shorter. Does that make sense? So I guess what you could call that is like you're being squished again, I guess. Squished shorter. Those are all of the different possibilities. And it either results of putting something inside a function like this, or it's a result of taking a function and putting the number on the outside of the function. So those are all your possibilities. Does that make sense? Okay. Let me go through my notes for the day then. Today, basically, we're going to take all of those functions and put them together. So rather than doing them one at a time, we're going to do, like, say, 3 or 4 of them at once. Okay. Here's all the different possibilities then. And there's a lot of different brackets. Okay. This A sitting on the outside is what causes things to stretch up. This B sitting on the inside is what causes things to pull in or out this way. This H right here causes things to go left or right. And this K causes things to go up or down. I think rather than focusing on this, let's just hop to an example. Okay. Actually, I guess I have pictures. So I guess one more time, if I'm being really redundant, I'm sorry. If this is, say, your original function, the -2 shifted it that way, the +2 shifted it that way. Fair enough? If blue is your original function, -2 brought it down, +2 brought it up. Okay, here's a trickier one. If blue is your original function, the 2 made everything taller. You see how the blue is right here? All of these points are now a little bit higher than they used to be. So if you like my Curious George mirror analogy, this is the mirror that makes you look really tall. However, if you put a 0.5 in front of it, all of the blue points are now shorter than they used to be. So that's the mirror where Curious George is now shorter. Does that make sense? Here, if you put a negative, you see how it takes the graph and it literally flips it on top of each other, like head over heels? This one's probably the trickiest one to look at. I think this one right here was the original point. If you made a 2, what it did is it actually took the graph and it shoved it in. But if you took a 1/2, the 1/2 actually pulled it out and made it fatter. So that one maybe is the one that's the most backwards. Is inside the brackets, a 2 actually shoves it in and makes you thinner. Or if you use a 0.5, 0.5 makes you fatter. Okay, let's do this example. Let's try to sketch this without our graphing calculator. Pretend that we had just a regular y equals x squared graph. What does an x squared graph look like? Basic old parabola. So don't draw this, just watch what I draw. There's a basic old parabola. What sort of movements does this graph have to undergo? There's 3. There's a -5, there's a +4, and there's a 0.5. So let's talk through what they do. What does a -5 do to a graph? It's going to go down 5, yeah. What is this +4 right here going to do? Sideways left 4. You're good. That's right, though. Yeah. This one's the new one. We didn't do this one until, well, yeah, this morning for most of you. What does a 0.5 do if it's outside the brackets? Good. That's a great word to use. It's going to expand it. The 0.5, until you memorize it and just know this, a 0.5 is the fatter mirror. This graph needs to become fatter. Here's the question. What order do we do all of these things in? And the answer to that is we have to do BEDMAS. You guys remember BEDMAS from, I don't know, brackets, exponents. Don't focus on that. Multiply and divide comes before add and subtract. Here's an add, here's a subtract. We should do those last. So this is a multiply. We have to apply this 0.5 first. So what I'm going to try to do first is I'm going to make the graph fatter. So if I make the graph fatter, probably look something like this. Does that make sense? That would be a fatter graph. And then the next 2 things I have to do, where's the select button, is I have to pick that graph up. I have to move it down 5. 1, 2, 3, 4, 5. And then you guys said this way 4. So I would expect that graph to look like this. It's going to be a fatter looking graph over and down. Fair enough? Okay, now let's grab our graphing calculators and check. See whether we've picked up on how this works. Just for some context, I'm just going to graph a regular x squared graph just so that I can see where it normally would be. And then I'll graph the 0.5 bracket x plus 4 close bracket squared minus 5. And just see what these graphs are about where I said they'd be. So there's your basic quadratic. Here's your other graph. Okay, I might have been a little bit too fat, I guess, with the red graph. But is it about in the right location? Does that make sense? Clearly, would it make sense that this graph right here has been pulled a little bit in the fatter direction? That's what that 0.5 did to it. I have a little blurb up here. It says, question, is the 0.5 inside or outside of the function? What's the answer to that question? Is it inside or outside of the function? It is outside, yeah. The reason why is that this 0.5 is on the outside of this bracket right here. Okay. The difference would be if I wrote it as y equals bracket 0.5x plus 4 squared minus 5. You see how the 0.5 is like inside that squared sign? If it was inside the squared sign, that would change things. Okay, let's try another one. Any idea what this base function would be? Do you guys remember what that line right there that means? Do you guys remember what an absolute value graph looks like?
It's like a V.
It's like a V. Good. Okay, so here's what my original graph would hopefully look like. What does this 3 right here do?
Change slope.
Go back and look at our notes here. What does, where did I write it here? If we had a 3 inside the brackets, it looks like this one right here. It's not a 2, but it looks like this one. What does this do to the graph? Everything got squished in. Does that make sense? So, what should hopefully happen for this one is this should now become a thinner looking graph. So the 3 should cause to look maybe like this. Justin used the word terms like changing the slope. That's kind of what happened here is this point right here got pulled in, and this point right here got pulled in, and this point right here got pulled in, and this point got pulled in. Do you see how everybody's got pushed? Everybody got pushed inwards. It kind of caused the slope, because everyone got pushed inwards, it caused the slope to become bigger. I like the example of like a car crusher, where it's like on both sides, it's squishing in. And just what ended up happening is it caused the graph to become a little taller. That's what the 3 does. What does the plus 6 do? Move it to the left 6. So I'm just going to literally pick this guy up then, if I can find the button that does that. And move it over 6. So I would expect to have a very thin looking V sitting way over here. Does that make sense? Let's test it. Do you guys remember how to do absolute value in a calculator? Okay, go second. 0 is catalog. And absolute value is the very first one listed, probably ABS. Okay, so let's just do the absolute value of X. I'm just going to graph that. There's our V.
Sorry,
Lost you there? Okay. So go second, 0 for catalog, and ABS is the very first one. If you have a newer calculator, it might actually put those like big lines on either side of it. Mine doesn't, so I have to type in 3x plus 6. Let's graph it. Let's talk through just what happened here. What did that 3 do? Did the 3 squish the graph in like a car crusher? Yeah, it did. That plus 6, though, was supposed to move the graph over 6, and it did not. How far did this graph get moved over? Maybe 2, actually. I think I moved over a little ways. There's a reason why this didn't work, and it actually, again, has to do with bed mass. The very, very first thing in bed mass is brackets, and 3x plus 6 can be written with brackets if you read it like this. 3 x plus 2. What did I just do there? I factored it. There's a very high chance that on the diploma exam, they're going to give you a question where they ask you about transformations just like we're doing right here, but they're not going to factor it. And that's meant to throw you off. The reason why this thing only moved over 2 is because, look, when you write it in a factored form with brackets, x is only being added 2. So that's why it only slid 2 that way. Does that make sense? So star, highlight this somewhere. When you're talking about all of this stuff, it has to be factored if possible. If it's not factored, then bed mass has not been applied properly, which means you don't have brackets where you possibly could have. Does that make sense? So, although I thought that it should be over here by 6, it actually should only be over here because there's only a plus 2. I did this one on purpose to hopefully illustrate a point. You've got to be careful for brackets. Okay, let's try this one. This one's got a mess. I mean, there is so much stuff happening here. So let's, before I go to the graphing calculator, let's just walk through all the different things that are going to happen. I'll start at the back. What is this plus 6 going to do? Actually, that plus 6 is way on the outside, so let's move it up 6. Did you see how this minus 5 is kind of like inside?
So it's kind of moved
Right. To the right is 5. Perfect. Okay. What about this 2 right here?
push it in.
Well, do you see how this bracket right here and this bracket right here are still before the square root?
On the outside, so it's gonna-
Actually, no, technically this 2 is on the inside.
oh, it is on-
So what did you say the first time around?
it's a compressed in.
Good, it is, yeah. The 2 is going to compress it in twice as much. Correct. However, what about this negative sign? Where's that negative sign located? Inside or outside? So what does a negative on the outside do? Does it flip it head over heels or side to side? Perfect. Okay. So we've got to do 4 things. We have to flip a graph head over heels due to that negative sign outside of everything. The 2 that's kind of inside that bracket is going to compress it in like a car crusher. The minus 5 is going to slide it over 5, and then the plus 6 is up 6. Last question, what's the function that we're talking about? Well, it's just a regular x squared kind of graph. So let me start with here's a x squared kind of graph. So, which one needs to get done first? You know what, actually it doesn't matter so long as it's not the add subtract. So for example, this negative sign, I could flip this graph upside down. I've now taken care of the negative sign. Does that make sense? And I also need to take this 2 right here and car crusher this graph in with a 2, squish it in. So it's going to make it look something like this one here. Why don't I use a different color though? So then the 2 would squish everybody in. And then last step, it now needs to be moved over 5 and up 6. So hopefully we're going to get a graph that looks something like this. It'll be an upside down, squished in, slid up and over parabola. Does that make sense? Let's graph it then if you haven't already. I didn't play any tricks on this one, by the way, so this one should work. Here's a regular quadratic, negative bracket, 2 bracket. Oh, by the way, do you guys see how this 2x minus 5 is in a factored form? Okay. As a twist, they could have written it as negative 2x minus 10 squared plus 6. Do you guys see how this thing right here would not have been factored? And so it's not supposed to be slid over 10, it's supposed to be slid over only 5. So x minus 5, double bracket, then square, then add 6. So here's our first parabola. And then hopefully over here we see a slightly thinner parabola, upside down, over and up. What am I doing? Okay, let's fast forward to some different slides then. Okay, why don't we do this one first? This one just asks us to put into words what would happen to a function. So how many different things need to happen in this graph? I'd say 4 things need to happen. There's a negative sign, that's going to do something. There's a 3, that's going to do something. There's a minus 4, and a plus 2. That makes sense. So let me write out, maybe in words, what's going to happen. The negative is going to reflect the graph head over heels. Does that make sense? Sometimes we say this means that you reflect in the x-axis. Sometimes that's the way they phrase it. So how the x-axis is the flat line across? Basically, it just means you're reflecting it on top of the axis. So head over heels. So that's one thing we have to do. What's the 3 going to do? Good, yeah, the 3 is going to make it taller. So the 3 might be stretch 3 times taller. That's another thing that will happen. What's the minus 4 going to do? Good, so maybe a word you might see is the word translate. That way by 4. And then the plus 2. Good. Up 2. That'll work. Why don't you guys try the next one? Without me doing it first. See if you can kind of write out the same sort of things I just did there. So the 2 in front. That'll work, yeah. So maybe a stretch of 2 times taller. Good. Perfect. You got it. Make sure you do it in that order though, okay? You don't move things sliding them left and right and up and down until you've done the stretching and reflecting. So you have to make sure the order is correct. You have to do the multiply, which is this 2. This 2 is being multiplied. Make sure you do those transformations before you do the 4 and the 1. How am I doing? You guys got any of this? Okay, let me just keep going and try to find something more challenging here. Okay, why don't we do this one here? One thing you may get asked then is they may give you a picture of a graph. And they can't ask you in a multiple choice question to actually draw where the graph would go. But what they could do is they could give you some different choices of pictures and say which picture is where the graph would end up at. Does that make sense? So we can't type this graph into our calculator. You know how like the first examples I did, if you had wanted to, you probably could have just typed the graph in your calculator and know exactly where it would be. Well, if I give you a picture like this, you can't type that in your calculator. But my question is, well, where would this graph end up at? So let's try the exact same thing we just did. How many different things do we have to deal with based on this equation here? 3. There's a negative sign that's going to do something, a 2 that's going to do something, and a 4 that's going to do something. However, it's not factored. Catch. You see how this 2x plus 4 is not factored? Brackets for bed mass have not been achieved first. So I really need it to be negative x, negative f, and then 2 with an x plus 2. See how it now has the right amount of brackets there because it's factored? This is a little bit easier for me to do maybe than you guys because I can kind of slide things on my table here. So I'm going to deal with this negative sign first because that's a multiplier. What does that negative do? Flip it which way though? Upside down or side to side?
Upside down.
Upside down or on the x-axis. Both are correct terms. So would it make sense that this point right here then would now come down to right here? You see how I've taken this point right here and I flipped it down to there? This point right here is going to get flipped down to there. See how I did that? And this point right here that was negative would get flipped up to here. So this is not done by any means, but this is the graph being flipped. So far, so good. Next, I need to deal with that first 2, the multiply 2. So I'm going to use a new color. What does this 2 do to a graph? Not 2 times taller. If that 2 was out front right here, that would make it 2 times taller. Good. It's but not like this way. It gets squished car crusher. Does that make sense? So I need to take all of these points and squish them in. Now, in means towards the axis, though. See how this point right here is at negative 2? It would move in here to negative 1. That is half as much. See how this point right here is at 3? It would come into 1.5. Do you see how this point here is at 6? It's going to come in and move in till 3. And so this is what happens to the red graph after it's been car crushed and squished in. Last steps, I can cheat a little bit. It needs to go +2 means to the left. So I've got to move this guy to there. I'll even try to move the dots too. I'll just get rid of the red stuff. Now you're not going to get asked to draw that on a test. Like I'll ask you to draw it once or twice on an assignment. But you would need to be able to pick out that if the graph was here, that's the correct answer for that. That make sense? Okay, let me do one more and then I'll let you guys have a break and we'll call it a day. Why don't we try this one here? This one looks like it has a lot of nice twists to it. Actually, no, let's do this one. I like the double negative twist. Okay, so there's actually 4 things we have to do here as well. There's a negative on the outside. That's going to flip it up and down. There's a 1/2 on the outside. What's that going to do? Which way though?
Up and down.
Up and down smaller. Yeah, it's almost like the car crusher is actually this way. This is the Curious George shorter mirror. That's what this 1/2 does. What does this negative do?
So is it like
Yeah, flips it in, I don't know, side to side.
on the line?
And then what does this 2 do? Squishes it car crusher in. So this 2 right here squishes it in. This 1/2 right here squishes it down as well. Does that make sense? So this one right here has to be a 1/2 to make it shorter. This 2 right here has to be a 2 to make it shorter. So let's do the trial of this. I'm going to do both of the negatives first, and then I'll deal with the squishings. So this point right here, I'm going to flip it up to right here. That's been flipped up. And then I'm actually going to flip it all the way across the other way as well. So I'm going to flip it over to here. This point right here, does that make sense? How I flipped it up to here. And then I also flipped it across that way. Now it's over there. This point here, I'm going to flip it down to right here. Where's the line? Here. And then I'm going to flip it over to there. I'm going to circle these just so I know which ones are which. This point right here, I'm going to flip it down to there. And I'm going to flip it over to here. I have a strong feeling that if this point flipped to that point over there, it's probably going to be this point flipping over to here, but let's just double check. This one could flip, let's say, all the way down to here, and then it would flip all the way over there to here. So here, is that new graph now? So it's been flipped over and upside down. Does that make sense what I just did? So those are the negatives. I still haven't actually dealt with the 2 and the 1/2, but I'll get to that. Now let's deal with the 2 and the 1/2. They both do kind of the same thing. One of them brings it down, squishing it like this, and the other one squishes it in. So I'm going to find these points and I'm going to cut them in half. So like, for example, this one right here looks like it has an x value of 8. If I take an x value of 8 and cut it in half, it would be over here at 4. But it also has a y value of 6. Cut that in half and it would be at 3. So what was at 8 and 6 is now at 4 and 3 because both of those numbers got cut in half. For different reasons though, right? This 1/2 right here cut the y value in half. And this 2 right here actually cut the x value in half. So this point has been moved to here. So far so good. Okay. This point down here, the y value is -6. So cutting it in half, it would be here at -3. But its x value is at 4. So that means it should be over here at 2. So this point right here is going to move to here. This one's maybe the trickiest one. It looks like it's got a value at a 1 and a 3. So I'm going to have to cut it into like, say, 1.5, right about there. And then it's going to have to go like to right about here. Does that make sense? I'm kind of pulling it halfway into there and then halfway up. And the last one. This guy down here was at 6. So if I cut it in half, now it's over here at the, actually, let's do this. The 8 cuts in half over here to 4, and the 6 cuts in half to about 3. So that would be halfway that way, halfway that way. Here in purple is where this graph would end up at then. That is a graph that has been flipped head over heels, been flipped side to side, and then 2 different car crushers. The 1/2 squished everything down a half, and the 2 squished everything in by 2. Does that make sense? Okay.
So one process.
It can be, yeah. You're not going to get asked to do, I mean, like I said, if they give you a question like this, they'll probably give you the original graph, they'll give you an equation, And they'll give you 4 pictures, and you just got to figure out which picture has the graph in the right place. Does that make sense? So ultimately then today's goal, if I go back to where I started, I think I'm going down for the day, is we can take equations and shove them inside of other equations, depending on how it looks, depends on how the graph moves. So if you put a negative inside the brackets, side to side flip, a negative before the whole thing, up and down flip. A 2 inside the brackets, squish in side to side like a car crusher. Put a 2 out front of the brackets though, make it taller. Put a +2 either inside or outside of the brackets though, adding and subtracting slides the graph up and down or left and right. So today's goal then was, well, let's put it all together. Sound good? Cool. Okay, take a break. When you come back, finish the second assignment or start on the third. So, can I have that second assignment by the end of the day? Is that, I guess it's pretty close to being done then?